writing it up, but the general idea is if we start with p local finite CW spectra of type n, where n is, that just means that the n is the smallest one where the Morava-K theory on it is non-trivial. You can build up what's called a VN map, which means a self map like this from the default suspension of X to itself, such that the Morava-K theory on it is an isomorphism at n. And otherwise is trivial. There's another part of it, which is why there's two things here. If I have two of those spectra such that they have their VN maps, we can form a nice little diagram. Such that we can find integers I here and j there, such that for any map on this bottom row, this triangle will commute. And implicitly, we have that di is going to be equal to ej. Now, before I actually go into the proof of this, I'd like to sort of motivate why we would want such a theorem to be true.
So the choice of f for every type n thing is functorial?
I believe that's what this is saying. Yeah. So if you get any choice of this, you'll see later on that different choices of VN maps are essentially unique in a way very similar to this, where if you get two different VN maps, some power of them are going to be homotopic. So you can think of it as functoriality, or I think Ravenel calls this extended uniqueness.
Can you remind us, or remind me at least, what the bar over Kn denotes?
I believe he uses that as reduced K. Yeah, nothing fancy. Just yeah, he uses a bar for some reason. I really don't know. So the idea behind this is that the periodicity theorem is going to allow us to sort of inductively construct type n spectra. So we can start with a type 0 spectrum. Thankfully, the sphere spectrum just covers this. Is that right? Possibly, or that's a Q there. But importantly, this is not 0. So immediately we already have a type 0 spectrum, just the sphere spectrum.
Isn't K0 star of a point pi star KO?
The homology on the sphere spectrum is going to end up being pi star. So the homology, which is important there, of the sphere spectrum, will give us the homotopy groups. To produce a type 1 spectrum, we can proceed very similarly. It is actually the mod P more spectrum. So if we get a degree P map between the sphere spectrum, and we take the cofiber of this, which is just a mod P more spectrum, this will end up having type 1. And you can see this because, importantly, this thing here is going to end up being a VN map. So I want to talk about that just a little bit. You can apply the Morava-K theories to this cofiber sequence. And I'm going to get very lazy now. Instead of writing all that out, I'm just going to write K with a subscript denoting the thing. If you have problems with that, please ask me. Now, the reason that this works the way we want it to is since this is multiplication by P, and since this thing down here is the finite field of P with these things adjoined, this map is going to end up being 0. And so you can see that the kernel of this map here would have to be the image of this thing here. What do I want to say? Never mind. The kernel here would be the image there, which means this thing here cannot be, this thing can't send everything to 0. This is an injective map demonstrating that K1 of this cofiber is non-zero. And similarly, you can use this to show that K0 of it is 0. So the K1 of this thing is going to end up being non-trivial, making this cofiber a type N spectrum. The point of the periodicity theorem is that you can do this over and over again inductively. The condition guaranteed over here is literally allowing you to just repeat this again and again and again. If I have a type N spectrum, we can get a Vn map F on that spectrum. And then this cofiber here will be a type N+1 spectrum. And so this is basically ripped out of Lurie's lecture note part 27. In my understanding, this is probably like the big reason you'd want the periodicity theorem to be true. So
using the periodicity theorem, you're able to construct whatever type spectrum you want.
exactly, exactly. And you can literally, starting easily bottom from S0, you just build it all the way up and up and up. And you just end up getting what you want because of this theorem. And now we start the proof of it. So the first part is not terrible. And the second part, Ravenel makes us work a little for it. I'll say that at least. It's going to proceed in 2 or 3 steps, which I'll just list out here. So first, we're going to say we can get a subcategory called Vn of just we just say, hey, it's a subcategory, all of which they carry a Vn map. We're going to demonstrate that this thing is a fixed subcategory. And by the fixed subcategory theorem, that'll allow us to classify it. And in fact, we're going to end up showing that it is on the nose equal to this subcategory FPN that we've seen before, which is just the category of Kn-1 acyclic spectra. Once we do this, we're going to actually see that this doesn't give us immediately it's this one. It's going to be either this one or this one. We don't know. We only have an inclusion that I'll show in a bit. Part 2 is actually going to do the legwork of constructing something in here that carries a Vn map. And that's the really hard part.
P, comma, N, specifically the ones that are not K and acyclic, or are they allowed to also be K and acyclic?
FPN, I have it down here. I'm 90% sure it's the acyclic ones, but let me verify. Do I have it down here easily?
Never mind. I think these are supposed to be filtration, right? So they can.
Yeah, exactly. This is the ones that are Kn-1 acyclic. Yes. And so, second part is actually constructing a type N spectrum with a Vn map. Unfortunately, this is the part where there are just not enough details to do it fully. The part that I'm going to really focus on is the way where he uses the atom spectral sequence to show a property that we'll see later immediately gives us a Vn map. The actual construction of the spectra carrying this property, we're not going to do. And also Ravenel just doesn't do it. He puts up things to appendices and goes to like other sources. It's not very useful. Okay, so before we actually go in showing that it's a thick subcategory, we should have some evidence for it being a thick subcategory. And in fact, we're going to show 2 inclusions. I want to make sure I get right because it was troubling to write down originally. Where did I have it? We're going to say that we're going to show that it's a subsection there, and we're also going to show that FP. It also goes like that. Which one is the easy one? This section is the easy one. If I know that it's Kn acyclic, then immediately the zero map is a Vn map, or the trivial one. So I can literally just collapse it to a point. Since this thing is already trivial, it's an isomorphism, and since it's trivial everywhere else, Kn of it has to be trivial. Boom, we've shown it's a Vn map. To show the other inclusion, we actually show the reverse or the contrapositive. If it's not in here, then it can't be in there. So in fact, if Kn minus 1 of something isn't trivial, then its type is immediately less than n. And from a theorem that I didn't talk about in my talk, but I was actually supposed to, there's a theorem that for modules over mu star, or really anything that you can do Kn stuff with, the fact that this being non-trivial immediately shows that no Vn map can exist. And this is due to the Landweber filtration theorem. So if we have something like this here, the immediate fact that this is non-zero would imply that there can't be anything algebraic that looks like a Vn map. And so there can't be anything topologic that looks like a Vn map. And I think this result that I'm specifically referring to is 3.1.1 in the Orange book, if I remember correctly. So we have these inclusions here. And so the moment we prove it's a thick subcategory, we'll automatically get that it has to be one of these two. And so that's the brunt of the proof right now. And just to remind everybody, a thick subcategory, at least in the case of helical finite spectra, or just finite spectra, whatever you want, is just a subcategory that satisfies two conditions. If I have a smash product in it, then the constituent spaces are in it. If I have a cofiber sequence, then this satisfies the 2 out of 3 property with respect to membership in this subcategory. So let's try to do it ourselves.
Is it also closed under smash product?
I want to say that a condition like 2 would guarantee it's closed under smash product. Yeah, I think if I give a trivial map into there, I believe the cofiber is going to end up being the smash product. Am I right in saying that? Like collapsing to like the base point of Y or something.
Trivial to cofiber.
I don't know. I think there may be a condition then. I don't remember seeing it in the definitions, but I also could have missed it.
You can say that we're trying to look at for specifically for thick ideals.
True. Yeah, you can restrict it. So yeah, possibly one of these do it, and if not, then we just amend the definition. But let's say that we know that this is something that supports a Vn map. And we get something along these lines. We're going to try to show that X is going to have a Vn map. We're not really going to make reference to the fact that we're using X, so it'll also work for Y. This, I think, is probably one of the more interesting parts of the theorem. It relies on this lemma So let's say that I have a VN map like that. We're guaranteed to find some iterative this such that to talk about something, you're way ahead now. So if we take this map here from the previous talk, we can form the Spanier-Whitehead dual of this. So Spanier-Whitehead duality would sort of take this map and produce from it something going from like the D section of the sphere spectrum into this section here. So it's going to end up being a homotopy class in here. And let's say that this adjoint here, if this is F, we'll just say that that's F hat. The lemma is going to end up being that there is some iterate of this map where it's in the center of the homotopy ring, stable homotopy ring. And this is what's going to allow us to sort of move around maps to demonstrate inverses.
Sorry, why is it a ring?
Because this thing is a ring spectrum. The identity map for any spectrum is going to induce a unit map into the Spanier-Whitehead dual. And then the multiplication, what is multiplication? At some point I remember doing this. It's discussed in Ravenel.
Oh, never mind, I see, it's the dual tensor with, oh, so just like the link account, okay.
Yeah, it's nothing too fancy. There's nothing really intense going on there.
But is the point is that it's like not a commutative ring?
Yes, it's very far from being commutative, but we can raise something like it to be in the center. So it'll commute with elements.
And the center means like the things that anti-commute?
I think it's commute on the nose. Yeah. Importantly, the reason we care about this is we can construct a self map on X in this following manner. Where this is just inclusion into the smash product. This right here is the VN map. And then this is just crushing down Y. Now, to show anything nice about this composite map, which I'll just call F prime.
Crushing down Y, what do you mean by that?
Like if it's the smash product, you take Y and just collapse it to the base point.
Algebraically speaking, like in the category of spectra, like this is a map from X smash Y to X smash the sphere spectrum. So what's the map from Y to the sphere spectrum?
I would assume, what is the map from Y to the sphere spectrum? I actually don't know. I didn't think about this. I was just assuming that it was something that looked like the smash product. I didn't really think too much about what's going on in the spectral level, to be honest.
Why can't it be the trivial map?
Oh yes, I think that does work. Yeah.
Yeah, you're just saying goodbye to Y, losing all possible information. That's the important thing here. So we end up with a map like this. Now, since we know that this VN map over here is an isomorphism on Kn, that's what we're going to try to do here. If I take Kn of everything here, I can form this terribly ugly sequence. And this composite here is just going to be Kn of our F prime. And then we can almost go backwards. Apologies, this is going to get possibly small. Okay, that smashed there, and then Write that a little bit bigger. Where this up here is just Kn of our F. And then this map here is the inverse. Now, because of the fact that this thing is in the center of that ring, this composite right here is just the idempotent. If I apply this more than one time, it's going to end up being the same. And we can commute this up here. So I can, instead of going immediately to the VN map, just perform the idempotent. And then I'll have the effect of the VN map here right next to its inverse. And immediately those will cancel out and basically give me a trivial map. I don't want to do it there. Oh. Importantly, that will give me a map like this, where it's going to be the identity on the Morava K theories. And this right here will show that the induced map on X is an isomorphism. Does that make sense? Are there any questions about that? Good.
What's the F prime again?
F prime is this terrible composite from the suspension of D down to itself, built out of the VN map on X smash Y. Yeah. And so that is sort of what Ravenel alludes to. And he's like, great, these things commute, we get our theorem. Just spelling it out a little bit what he means, because he has a hard time doing the details. Now, if we have a cofiber sequence, if we have a VN map here on X, because I want this to be H now. That's just sigma D H. If I have two VN maps like this, we can complete this over here to get a diagram. This is just, I believe, something about cofiber sequences. Nothing too VN-y going on around here. Let me make sure I know where I'm at. This is where the second part of the periodicity theorem comes in, where we do all of this extended uniqueness stuff. The lemma that's going to be important here is that we can do the self-map thing.
Bottom right corner really CH or?
It has to be something like C, suspension D of H, something along those lines. Because of that second part of the theorem, we can find integers like this always, so that this thing really does commute. And secretly, we're just going to replace them. So if I needed an f to the I here, we're just going to pretend that this was f to the I all along, and that this d is modified correspondingly. These lemmas will, some of them will be proved in the end of the section. The ones that I think were interesting will be proved. And so you can immediately apply K to this. And then you just end up with basically a 5-lemma argument. This thing is an isomorphism because of the VN map. Same here. Phi-lemma shows that that has to be an isomorphism. Now, it would be great if this could also show that for n different or m different than n, it would be trivial. Unfortunately, it does not. That is why we have to replace this induced map here, which I think I forgot to label.
Not make zeros on the end there, should we? I mean, it should be a long exact sequence.
Yes, you're exactly right. You can continue the long AX sequence and just slice it off. So thank you very much. I think, did I put zeros here originally? I don't think I did. Let's go me. Exactly, yeah. I like writing zeros and I accidentally wrote them there. So thank you for pointing that out. Would not have been good. Instead of just having this one map L here, we're gonna be very, very pedantic. I'm gonna sort of start avoiding writing things. Fill in the spaces here, you know what they are. I can perform one VN map to desuspend down by D. I can again perform another. Applying this twice, getting L squared is actually gonna be the thing that's trivial, and that's because of a diagram chase. The idea is continuing this cofiber sequence, we'll have that a map here is 0. So I have an element X in here that is gonna be in the Morava K theory applied to like the 2D-fold suspension of the cofiber. If I have an element in here, we know that going down to here, it'll have to go to 0. That's just because this map over here is going to be 0. And again, over here, I guess to be explicit, this is going to be something like this. Now, if I call these maps, this is going to be from that to there. This is something like a boundary map. That means that the image here is going to be in the kernel there. That means that it has to be in the image of this map here. So that means that there's something in here that'll project to the same thing. And if I follow L twice, that's going to be the same as taking this element and moving down here. But that map is also a 0 map on Kn. And so through this diagram chase that I sort of abridged a little bit, it'll automatically show that L squared of any element X and what we care about will be 0. And there, that means L is going to be the VN map we want. Sorry, L squared. That's the whole point. For the diagram chase, should I make anything more explicit or is it good enough? Very good. And this right here shows that it is a thick subcategory. The thing I've erased show that it's closed under smash products, or at least the version that we used. And you can replace this cofiber sequence by moving around to show that it satisfies the 2 out of 3 property. And so boom, it's a thick subcategory and it has to either be FPN plus 1 or FPN. And now we get to the part of actually constructing these things. Interestingly, for all that Lurie likes to write 1,000-page books, he probably did the most sensible thing in his lecture note and just chose not to prove this. Which is very surprising to me.
He does that in his books as well.
Yeah,
Still very long.
I will not understand that man. But I'll understand him for this. Thank God he didn't choose to do this. So there were 2 lemmas over there that I didn't end up proving. Were any of them interesting? No, I don't really think they were. There's possibly interesting proofs in the lecture notes. You can choose to go to them if you so desire. So here we actually go about the construction. And this sort of goes through the atom spectral sequence and the Margolis homology groups. I hope I'm saying that right. I'm probably not. The idea for this section is we're going to sort of slightly strengthen the condition. So instead of looking at just type N spectra, we're going to pass to this thing called strongly type N. There's going to be a result that I'll just appeal to that'll show that these spectra they make the atom spectral sequence simple enough. And then this is going to provide our VN element.
I'm guessing strongly type N is stronger.
I think there's an equivalence that goes both ways. And I also don't believe Ravenel might talk about it in section 6.3.3. But like I said at the start of this talk, I didn't really go through all that route because the proofs are just Not very enlightening. Yeah, you're exactly right. There has to be some passage from a type N spectra into a strongly type N spectra. In fact, if you read the section, there's also like a weakly type N spectrum, and you need a passage from weakly type N to strongly type N. There's a lot of passages. And at least for that second one, he just doesn't talk about it at all. But before we start, since the atom spectral sequence is over the Steenrod algebra, we're just going to remind ourselves what that looks like. For these different primes, the actual Steenrod algebra, if I remember correctly, is Z generated on beta, and then these P's, actually no, sorry, this is just Steenrod squares. And the dual Steenrod algebra has a description as generated by these psi elements. Over here on the P is not two side. End up getting some beta element as well as these P elements. I can't write a calligraphic P, so go with me here. These are going to be the calligraphic P's. And in the case that it's not two, this is, what is it? It's like C mod P. Generated by these C elements again. Tensor with a symmetric algebra on these taus. E is the symmetric algebra generated, right?
Some people use it for exterior.
Lovely.
So
Yeah.
I would use this use lambda.
Exactly. Why wouldn't you? I don't know. He uses E. I don't know what he means by E.
The Steenrod algebra piece that's E over FP.
Probably. Probably these are FPs. Yeah.
Does he say symmetric algebra or does he just write E?
He just writes E.
So I think it's exterior.
Lovely.
And one of them is symmetric and one of them is exterior. I mean, the first one is a polynomial algebra.
Exactly.
The second one is the
It's
exterior.
exterior. Yeah.
Okay. So E. There you go. Question answered. E is the exterior algebra. If we have those things here, we're going to construct other elements. There's going to be these elements. What are they? P T to the S, that he calls it, as well as QI. If you treat, what do I want? These as the monomial basis for the dual Steenrod algebra, this thing is going to be dual to, what is it going to be dual to? This is the dual of this psi element, and this is going to be dual to just tau I. Thankfully, the specifics of these literally do not matter at all. All that's important is that since these are going to be elements in the Steenrod algebra, they are operations on cohomology and will allow us to form these things called Margolis homology groups. You can basically use these to construct a chain complex. The way that this will look is for a algebra over the, or module over the Steenrod algebra. This is the QI Margolis homology group. And this is the PST Margolis homology group. And importantly, I can put in the cohomology of a space in there. And so if I put a space in this slot instead, it's just implicitly that this is the cohomology of it. To my understanding, in the proofs that I will discuss, the specifics just do not matter at all. I think there's one lemma that I don't discuss, and that's just because it's very ugly. But we start with this. These things allow us to give the definition of strongly type N. I spelled that wrong. So a spectrum is strongly of type N if we have the following. The T plus S. And what is the Q on? So these are the three conditions. We have some vanishing on the Margolis homology groups. We can get that QI acts trivially on the homology groups, and that these two groups here have the same rank. And these end up simplifying the atom spectral sequence to a very, very big deal.
Sorry, do you define the Margolis homology group?
Nope, not at all. You can look in Ravenel for it. I believe it's only used in the proof of one lemma, the actual specifics of the Margolis homology groups. For the actual, like for this section, my idea was to give an example of how the atom spectral sequence can be used to do things. And to that end, the actual specifics of the Margolis homology groups just do not matter. Again, that's in Ravenel. Basically, these things act almost like a boundary in a chain complex, and you just multiply them the right way to get it. So with all of that, there's a lemma that Ravenel just appeals to from the work of atoms. I have a strongly type N spectrum Y. There is an insane amount of vanishing that goes on in the E2 term of the atom spectral sequence. So if I have E2 of S comma T, for this term, this is going to end up being 0 whenever S is greater than for some constant C. So you can imagine that if we picture the atom spectral sequence with this kind of a format, above a line that looks like this with slope 1 over, turns out this is the order there. Above this line, all of the X terms are 0. So immediately this is a vast simplification.
Does C depend on P?
C depends on, yeah, I think there's an implicit dependence on the spectra and of P.
So what is it constant with respect to? When you say constant, or do you just mean like a number?
Yeah, it's just some number. It'll probably depend on the P here, the spectrum there. Thankfully, it will not depend on S and T, or else this wouldn't make any good sense. It's just the fact that for this kind of a sequence, we have some sort of an intercept where we can make this line.
People call this a vanishing line.
Exactly. And above that vanishing line, things vanish, hence being called a vanishing line.
So I'm assuming that the Margolis homology groups that are just conditions on how this particular X group interacts with some specific elements of the scheme right after.
I would assume so. Thankfully, Ravenel does actually provide references of these works. I want to say it's like Adams and Margolis, 1968, but I could be completely lying about the year. Yeah, Adams and Margolis did work. They got these things, and we now use these things. Now, there's also another line down here that'll also have some information, and this is sort of what I want to describe. So like we saw, the Steenrod algebra was generated by these elements beta and these powers that I can't write for my life. We're just gonna say, I wanna have AN here be the subalgebra generated by beta p all the way up to this thing p to the n minus 1. And this is basically going to allow us to approximate around the above that line over there with this filtration. In the sense that this lemma provides, make sure I get this right. All that in there is the same. This is going to end up being an isomorphism if S is greater than again, this is some constant depending on n here, where n is sort of the level of the filtration. And as this filtration level goes to infinity, this approximation gets really good in the sense that the intercept goes to infinity. So that means that above this line, all of this behavior looks like that filtered subsection. And that is the proof of that lemma in in Ravenel is where the Margolis homology groups are used, I believe.
And does that paper also prove that there's this strongly typed spectrum?
No, that is in 6.3.2, he gives a construction of a weakly type n spectrum that's like related to the classifying space of ZP, which I'm not going to go over here. And then there's this thing called the Smith construction, which to my understanding takes a weakly type n thing and produces a strongly type n thing. Yeah.
And I'm guessing a type n thing produces a weakly type n thing. Because you need to go from type n to strongly type n.
Exactly. Yes, I believe that's how that goes. And the strongly type n thing that I erased, those last two conditions were sort of easy conditions to have, while the first one was really strong. So that's why you do the weakly type n, it weakens the first condition. I wouldn't be surprised if that weakening is what allows you to go from type n to weakly type n.
Technically, we don't really need to go from type n to anything else. We just need to prove there exists something of type n that satisfies this.
Doesn't the theorem say given a type n thing, you're producing that?
Yes, but the point is that it's a fixed subcategory, and we know it's either Fn or Fn plus 1. So if there's even one thing that is of type n, then it has to be Fn.
Exactly. That was the reason that we started with a fixed subcategory. This means we can just produce one thing, like Daron said, and we can get everything we want for free. Free with a lot of asterisks, I should say. But we can build sort of a diagram relating these approximations. This is just going to be inclusion of ZP into, you'll see in a sec, For the work of the atom spectral sequence, just like we did when we were talking about proving thick subcategories, we're really going to work with dy smash y, where elements of this homotopy group are going to correspond to self maps, and those self maps can be the Vn thing, as we're going to see in a sec. So we're going to move down here. This ends up becoming x of an with respect to zp. This is x to n with right homology groups. This is x over EQI, again, of these same groups. This is also another point of notational confusion that I had. I truly don't know what he means by P here, like P generated by an element. I looked everywhere and I could not determine what he meant by this. So if anybody has any ideas, please tell me. I was very confused. He just brings us out of nowhere and doesn't talk about it at all.
Might simply mean there is something you can put there.
I think there's something specific, which is, because I'll say in a second, the reason it's something specific is because the computation of x over that alternating thing of this group is isomorphic. Oh my God, isomorphic. I can't talk today. Isomorphic to this P thing.
Is it sufficient to say that's the definition or not?
It could be. I think there's also this part here, this isomorphism, where instead here you have the H star R. This isomorphism here is because the EI or the QI acts trivially on the cohomology groups. So I'm assuming that there's something specific about this thing that allows you to sort of take that tensor out there. And Ravenel just doesn't say what this P thing is at all. So I truly don't know. It may be something you can just take its definition. I really don't know.
That seems like a very odd definition.
Exactly.
It doesn't have anything to do with the end.
Exactly. I just, oh, Ravenel. Yeah, this is a commutative diagram. Nothing in here is assumed to be exact, but the importance is that for all n greater than or equal to some small n, which is the type, there exists some fancy element in x of an with a zp at the start, such that if this is phi, that's lambda of x is Vn to some power. One thing to note, Ravenel has this as H star of R. I don't believe that's right, which is mainly because he uses I of x, and then that'll get you something down here. He says that's equal to some phi of y, because it's in the isomorphism range, and I'm running out of time. But suffice it to say that this x thing here, this is also something he doesn't prove. This x is what I like to think of as a universal Vn map. Because of this condition here, we get that any power of y is going to act like the Vn map we want. And importantly, y is going to live here, which is the E2 term of the atom spectral sequence. Pushing it down makes it look like multiplication by power of Vn. But unfortunately, this thing by itself is not a permanent cycle in atom spectral sequence. What you can do, though, is you can take a sufficiently high power of it, and that will necessarily be a permanent cycle in the atom spectral sequence, for reasons because Y is in this range where things are central.
That said something in the chat that I was thinking, which is maybe P just means polynomials, so like polynomials on the
That would, I feel like that would make sense. I don't know why he didn't just put a Z there then.
Yeah, it's the complement to the exterior part, the polynomial part.
Oh, there you go. I don't know why he couldn't just put a Z there, but thanks, Ravenel. But in any case, because of the fact that this thing works, Y here is going to end up being our VN map for a strongly type N spectrum. And yeah, that is the usage of the atom spectral sequence. There's a bit more in the lecture notes that I had, but I think I talked about all the proofs I want. Are there any other questions about other things? Very good. Slash, were there questions in the chat that I were not able to see?
questions on Zoom. Okay, I'll stop the recording.
Sounds good.